Hello everyone, welcome back. We are in lecture 3 of week 6. In the previous lecture, what we studied is the relation between stress and strain. Now, in today's lecture, we are going to explore how the material fails under the action of different stresses, right? But before we move into the details, let us recall the stress-strain behavior that we discussed at the very beginning of this course, right? If you recall, we have different types of materials, either ductile or brittle. Now, for ductile material, the stress-strain behavior you can see on your screen. And we discussed in detail how we got this stress-strain behavior and what are the meanings of different regions within this diagram. But today, let us focus on this point A and point B. Now, this point A is the proportional limit. That means if we start from 0 where there was no external loading and then we apply the load, obviously, as the material is elastic, so if we load, it will follow this path, and once it reaches point A and if we start unloading, it will actually come back to its original position. Okay. Now, if we cross this point A, up to this point B, there is a chance of coming back without any permanent deformation. However, once we cross this point B, which is called the yield point, there will be permanent deformation in the material. And we definitely do not expect to have permanent deformation in the material, because if it is well within this proportional limit, we can load and unload the structure and use the same structure without having any permanent deformation, right? So this yield point, where the stress is sigma y, is actually the point crossing of this point. We consider it to be a failure. Now, this term failure should be carefully used. It doesn't necessarily mean the collapse of the structure. That means if you have a material, if you load the material, crossing a certain point here, our point of interest is B, is what we call failure. That means we will not allow any permanent deformation within the structure. Now, how do we get this sigma y? For that, again, we have uniaxial tension. If you recall, we discussed this. So we apply a force P at the ends, and then we measure the stress and strain, and we keep on increasing P, and then we can plot this. A schematic diagram is given here, right? Okay. Now, if we keep on applying this load P, at this particular point, the material breaks, right? And if you look at the failure mode, you have this type of planes along which the material fails, which is at 45 degree. Okay, and if you recall, maximum shear stress is actually at an angle of 45 degree. We discussed in detail in our earlier lectures, right? Okay, so with that, let us move forward. So if we have a material exposed to 3D stress field, so we have sigma xx, then tau xy, then tau xz, then sigma yy, tau yz, and then sigma zz. It is a symmetric matrix. Now, once we have this, we can actually do an eigenanalysis and then find out sigma 1, sigma 2, and sigma 3. These are the three distinct principal stresses, and the maximum value of the principal stress is sigma 1 and the minimum value is sigma 3, right? So the first theory that we have is maximum principal stress theory. So maximum principal stress theory. So we have sigma 1 greater than sigma 2 greater than sigma 3, and out of these three, sigma 1 is maximum. So sigma 1, if it is greater than equal to sigma y, obviously we call it a failure. That means sigma 1, which is the applied stress, so this is the applied stress, and sigma y that we get from the uniaxial test, this is allowable. So if the applied stress is more than the allowable stress, then obviously the material fails. And so long this applied stress is less than the allowable stress, in our case it is sigma y, then our material is safe, right? So that's the maximum principal stress theory. The second theory that we are going to discuss is maximum shear stress theory. Again, the three principal stresses are sigma 1, sigma 2, sigma 3. And if you recall the Mohr circle, from that Mohr circle we get tau max, and tau max has the expression sigma 1 minus sigma 3 by 2. So this stress, maximum shear stress, if it is more than the allowable shear stress that we get from the uniaxial test, then obviously the material fails, right? So how to get that limit? We can, in this expression on the right hand side, if you put sigma 1 equal to sigma y and sigma 3 equal to 0, then we effectively get basically the sigma 1 equal to sigma y, that is the maximum limit of shear in case of uniaxial test. So this is sigma y by 2. Or in other words, we have sigma 1 minus sigma 3 is greater than sigma y. If that condition is satisfied, this is failure, right? So that is the maximum shear stress theory. This is also called Tresca yield criterion. Okay, the next theory that we are going to discuss is maximum elastic strain theory. If you recall, epsilon 1, epsilon 2, epsilon 3 are the three principal strains corresponding to sigma 1, sigma 2 and sigma 3. Now, if you look at the maximum elastic strain, so we have epsilon 1, and the expression for epsilon 1, if you recall, is 1 by E. Then within bracket we have sigma 1 minus nu times sigma 2 plus sigma 3. Okay, now what is the allowable limit? Again, we can easily find out. For the uniaxial test, we put sigma 1 equal to sigma y and sigma 2, sigma 3 equal to 0, and immediately we will get sigma y by Young's modulus is the limit. So if the maximum elastic strain is more than this allowable limit, then obviously the material will fail. Now, if we further simplify, we can reduce this term capital E on either side, and what we get is sigma 1 minus nu times sigma 2 plus sigma 3 effectively is greater than sigma y. So that's the condition. Now, if you look at this expression, obviously when we deal with a three-dimensional body, due to this Poisson effect, we have sigma 2 and sigma 3 are the two more orthogonal stresses with respect to sigma 1. Obviously, due to this negative sign, effective stress will be less than this sigma 1, and this combined stress should be greater than the allowable limit, and that is sigma y. Now, if we go back to the maximum principal stress theory, obviously it says sigma 1 should be greater than equal to sigma y, but for a three-dimensional structure, obviously this is not realistic because of the Poisson's ratio. We'll have the contribution of sigma 2 and sigma 3, and from that perspective this expression is more realistic compared to what we have earlier. So this expression is more appropriate when we deal with three-dimensional structure compared to the first theory that we have discussed. So this is actually the third theory. So the fourth theory we have is called octahedral shear stress theory. If you recall the definition of octahedral shear stress, we deal with a plane which is equally inclined, right? So nx equal to ny equal to nz is equal to 1 by root 3 is actually the plane corresponding to this octahedral stress, right? And the expression for tau octahedral is 1 by 3 within bracket we have sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square whole to the power half. So that's the octahedral shear stress. And if you further simplify, this expression becomes root 2 by 3, and then we have I1 square minus thrice of I2. I1 and I2 are the two stress invariants to the power half. So that's the applied octahedral shear stress, and we have to evaluate the limits from the uniaxial stress, and for that again we can easily find it out. So what we do, we put sigma 1 equal to sigma y and sigma 2 sigma 3 equal to 0. Then if we do that, what we get is root 2 by 3 times sigma y is basically the limit, and if your tau octahedral is more than this value, the material fails, right? Now, the condition then, what effectively we get is I1 square minus 3I2 is greater than equal to sigma y square. So that's the condition for octahedral shear stress theory. So the moment we start with the 3D stress field along the octahedral plane, if this condition is satisfied, then again we will have failure. So if the left hand side is less than the allowable stress, which is sigma y, then as per this condition the material will remain safe, otherwise it is bound to fail. Okay, now before we move further, let us recall, if we have sigma 1 equal to sigma 2 equal to sigma 3 equal to say minus p, then corresponding tau octahedral is what? You can easily check from this expression. It will be tau octahedral is equal to 0, right? So as per this theory, if this condition is satisfied, there will be no failure because tau octahedral is 0, right? Keep that in mind. In reality, material can actually withstand large amount of stress before failure, right? So that's an interesting phenomenon that comes from the tau octahedral, or in other words, octahedral shear stress theory. Okay. Our next theory will be maximum elastic energy. Okay. So let us consider a small volume and then on each face we apply normal stresses. So we have sigma 1, sigma 2, and then sigma 3. Okay. So along sigma 1, we have epsilon 1. Similarly, sigma 2, sigma 3, we have epsilon 2, epsilon 3. Okay. Now, because of this strain along 3 orthogonal directions, we'll have change in dimension. So along this, say, change in dimension over the original dimension delta x, then delta y, and then delta z. So the change in dimension is delta of the original dimension, right? Now, if we have the stress strain plot, for linear case, we have a straight line and the area under this curve, which is here, this is the work done, right? So let us quantify the work done. In our case, we have half. So area under this curve is half times sigma epsilon. So let us consider, say, sigma 1, and it is acting over a face of delta y, delta z, and the respective elongation is delta x, right? Similarly, we can also consider 2 other faces, sigma 2, and for that we have the projected area delta x times delta z, and then the variation in length. Third one is half sigma 3, then corresponding area times the elongation. Okay. Now, what is this change in length that we can easily quantify? It is epsilon 1 times delta x. So what we get here is 1 by E. Within bracket, we have sigma 1 minus nu times sigma 2 plus sigma 3 times delta x. Similarly, we can also quantify the remaining two. Okay. And then once we quantify all these elongations along three orthogonal directions, we can actually further quantify the work done, and we can quantify the energy stored per unit volume, right? Okay, so let us do that. For that, we again focus on this expression. There, if we put the expression of this effective elongation over initial length of say delta x here, then for all three, we can use the expression and then further simplify this delta w, right? So if we do that, our delta w will be equal to 1 by twice E, within bracket we have sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 nu. Then within bracket we'll have sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 1, then multiplied by delta x, delta y, delta z. That's the initial volume, right? So if we find out U, that is delta W by delta V is equal to 1 by twice C within this hard bracketed term. Okay. So that's the energy stored per unit volume. And then we can again find out the limit from the uniaxial test, and for that again what we'll do, we'll put sigma 1 equal to sigma y and then sigma 2 and sigma 3 equal to 0 in this expression. Then we'll get the limit, and that limit is 1 by twice E times sigma y square. Okay. So that's the limit. So this third bracketed quantity with 1 by 2y should be greater than equal to the allowable limit. Or in other words, the condition that we get is sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 nu within bracket sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 1 is greater than equal to sigma y square. Okay, so that's the criteria for failure as per maximum elastic energy theory. Okay. The next theory that we are going to discuss is energy of distortion theory. Now, if you recall, the state of stress sigma 1, sigma 2, sigma 3, right? So, if that is the state of stress, we can resolve it into two components, and the first one is again PPP, that is the isotropic stress, and the remaining will be sigma 1 minus P, sigma 2 minus P, and then sigma 3 minus P, right? And if we satisfy a criteria, P is equal to I1 by 3, then that's the condition for first invariant to be 0, and that will lead to a state of pure shear. So, it will be a state of pure shear. Okay. Now, corresponding to strain also, we can write down the expression. So, it will be epsilon 1, epsilon 2, epsilon 3. And on the right hand side, we'll have, say, epsilon, epsilon, epsilon plus epsilon 1 minus epsilon, epsilon 2 minus epsilon, and the third one, epsilon 3 minus epsilon, right? Okay. And obviously, this first component for the strain is again epsilon 1 plus epsilon 2 plus epsilon 3 divided by 3, right? That's the average strain. Okay. Again, if we satisfy that criteria, so this will be a state of pure shear. Now, we have epsilon 1 having an expression we already know, it is 1 by E within bracket sigma 1 minus nu times sigma 2 plus sigma 3. And then similarly, we can also express epsilon 2 and epsilon 3, right? I'm not writing, you can easily identify the expression, right? Now, if we find out epsilon, which is actually here, you can see this one, then that epsilon is nothing but 1 by thrice E. Within bracket, we have sigma 1 plus sigma 2 plus sigma 3, and then minus twice nu, we have sigma 1 plus sigma 2 plus sigma 3. If you further simplify, what we have here is 1 by E, and then we have 1 minus twice nu times P, right? And that's effectively the proportionality of strain and applied stress. Now, if you look at this expression and just consider the first part, we can find out the work done, say W1, this 1 stands for the first part. So it is half times stress P, and then strain is epsilon. We have 3 such applied stresses along 3 orthogonal directions. So the total expression will be this one. Effectively, this is E by 2 P times epsilon. And this is obviously per unit volume, right? So what we get W1 is 3 by 2 times P, and in place of epsilon, what we can write is 1 by E, and then we have 1 minus 2 times nu times P. Okay. Then further simplification is possible because we know the expression of P, and if we do that, we get 1 minus 2 nu divided by E times we have sigma 1 plus sigma 2 plus sigma 3 divided by 3 whole square, and we have 3 by 2. So effectively, we can take this 3 out and further simplify. So we'll have 1 by 6. Okay. So that is, say, U1, energy corresponding to the first part, and then we will find out the energy corresponding to second part, U2, is nothing but the total energy U minus U1. Now, the first part we have already identified. So if we go back to the previous theory, and you can see here we have that expression of U, right? So if we use this expression, we can now find out the energy corresponding to the second term, which is here. Okay. So that we'll do in a minute, and that will be the energy corresponding to the distortion due to the state of pure shear. So if we do that, what we have 1 by twice E, then within bracket we have sigma 1 square plus sigma 2 square plus sigma 3 square minus twice nu, then we have sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 1. Minus, we have the expression for U1, which is 1 minus 2 nu divided by 6E, and within bracket we have sigma 1 plus sigma 2 plus sigma 3 whole square. So that's the expression corresponding to the state of pure shear. So this is the distortion energy per unit volume, right? Okay. Now we can simplify this expression because we can see 1 by twice C, we can take it out, and then further if we simplify, we get U2 in a compact form, and U2 is 2 times 1 plus nu divided by 6E. Then within bracket we have sigma 1 square plus sigma 2 square plus sigma 3 square minus sigma 1 sigma 2 minus sigma 2 sigma 3 minus sigma 3 sigma 1. I repeat once more, we have this expression for U2, and if you open this bracket and further simplify, you'll get this expression, and I leave it as a home task. Just check it at your end. It's very simple. Not only that, if you recall, G we derived in the previous lecture is E by 2 times 1 plus nu, right? So effectively what we have here is we can replace this expression, and then what we have is 1 by 6g. Okay. Then further simplification is still possible. If we do that, we'll have 1 by 12g, and within bracket we can further simplify sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square. Again, I leave it as an exercise. It's very simple. Earlier also we derived this expression, so you can easily cross verify it. Okay. Now again, for this case, we have to find out the limit from the uniaxial test, and for that again we will put sigma 1 equal to sigma y and sigma 2 sigma 3 equal to 0. And if we do that, our uniaxial is 1 by 6g times sigma square. That means the failure criteria is sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 1 whole square plus sigma 3 minus sigma 1 whole square should be greater than equal to 2 times sigma y square. Again, if you recall the expression of tau octahedral, which is nothing but if we take 1/3 of this quantity and square root of that is basically tau octahedral, and to equate that, what we do, we divide it by 3 and then whole to the power half. Right. So effectively what we get on the left hand side, we have tau octahedral is greater than equal to root 2 by 3 . Now, if you recall the expression of tau octahedral is equal to 1/3. Within bracket, we have sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 1 whole square plus sigma 3 minus sigma 1 whole square to the power half. So what it means, this, from this expression, what we get is 9 times tau octahedral square is greater than equal to 2 sigma y square. That means we have tau octahedral is greater than equal to root 2 by 3 sigma y. It's effectively the same criteria that we derived earlier for octahedral shear stress. Okay. So this condition is called von Mises yield criteria. So with that, let us conclude our discussion on different failure theories. What you have noticed is we start with the 3D stress field and then we quantify principal stresses, and then we find out the maximum conditions and equate it to the uniaxial test, and then we derive different criteria that quantifies the failure of a material. And that's how we developed all these different theories, and some of these theories, they agree with test results very well. Some of these theories are very conservative. For example, if you recall the first theory, that is maximum principal stress theory, we discussed that was very conservative because we consider only the maximum value of the principal stress, which is not the realistic case, because if you have three orthogonal directions with sigma 1, sigma 2, sigma 3, because of the Poisson effect, you'll have the contribution of sigma 2, sigma 3. However, if you come to the other theories, for example, this von Mises criteria, this is corresponding to the second part of the two components. We separate the original stress field. First one is the hydrostatic component and the second one is the deviatory component, and under special conditions it becomes a state of pure shear, and that actually distorts the material, and from that we derive this criteria, and that's how we develop different failure theories. So what we'll do, we'll conclude with one small example, and that will give you an idea how these failure theories are used for the purpose of design. Okay, so we have one small example. Say we have a state of stress where we have and then the shear stresses let us consider this to be negative. Obviously, if it is negative, there will be a opposite direction, but I mean the state of stress is given by 44.54 minus 5.13, then we have this is 0, right? Okay, so let us just consider a brief example. So we have a state of stress which is shown here. So we have (43.95) and then this is 5.13. So for this state of stress, if we find out sigma 1, it will be 44.54, and then sigma 2 is minus 0.59. And let us consider the material sigma y to be aluminium. So these are MPa, and sigma y is 95 MPa. So what we do, we apply Tresca yield criterion. For that, if you recall, this maximum value is 1 by E times we have sigma 1 minus nu times sigma 2 plus sigma 3, and that should be greater than sigma y by Young's modulus, right? Now normally what we do in case of design, we introduce a factor of safety, say n. Okay, now we check this factor of safety. So in our case we have n is equal to sigma y divided by, we have sigma 1 minus nu sigma 2. And then if we apply the values, what we have 95 as the allowable stress, and then we have 44.54 minus, say, Poisson's ratio 0.31 times we have minus 0.59, right? And if you do that, you get a factor of safety. So it is 95 divided by 44.72, and the factor of safety is 95 divided by 44.72. So this is 2.1. Okay. So it is more than 1. Okay. So in this design, we have factor of safety more than 1. Similarly, you can also apply a different yield condition. Say if we apply von Mises criteria, then let us solve this and see how much factor of safety we get if we apply von Mises criteria. For that, if you recall, von Mises criteria is exactly same what we derived for octahedral shear stress, and the von Mises criteria. What is that? We have 1/3 within bracket sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square to the power half should be greater than equal to root 2 by 3 times sigma y, and if we apply a factor of safety of n, we get this condition. And for the limiting case, we have this condition. Then we can further cancel this 3, and then we have n, which is equal to root 2 times 95 divided by, we have 44.54 square plus 0.59 square plus 44.54 plus 0.59 whole square. Now, if we just neglect this small component, what we have is root 2 times 95 divided by 2 times 44.54 square. So there will be a half here. So there will be a half here. Effectively, what we have 95 divided by square root of 2, then 44.54. And if we solve this expression, we have 95 divided by 44.54 divided by square root of 2. So we have 1.5, and again it is more than 1. So we have factor of safety more than 1, which means the design is safe, right? Okay, so that concludes our discussion how we can use the failure theories to design a material against its allowable stress, right? So try to solve the problems for this week, and if you have any doubt, do let us know, and then we will clear your doubts, right? Thank you very much.